Hey everybody, my name is Andy, and in this video I'm going to cover the various different metabolic equations that most of our health practitioners use to predict what your resting metabolic rate is.
So as you can see here, this presentation is primarily titled Find Your Metabolism. Again, we're going to hammer out some of the different math models that's come around throughout the ages and talk about what's good about them, what's bad about them. But first thing we need to identify is there is a difference between metabolism, bioenergetics, and essentially what the RMR stands for. So metabolism is the blanket term for the sum of all chemical reactions within the body. That doesn't just relate to bioenergetics, which is defined as the body's ability to consume foods into energy. That's a little more specialized in metabolism. Other concepts of metabolism is the way how our bodies develop hormones, the way how we develop fecal matter throughout the GI tract, the way how we uh, create neurotransmissions. Those are all different variations of metabolisms. But in this video, primarily the scope is going to be put up against the resting metabolic rate, or the RMR, which is the predicted amount of calories used in resting conditions, right? So other concepts that don't typically apply to this video, but will probably be presented in the future, are the total daily energy expenditure, also known as the TDEE. That's when we take a further equation model to predict how active a person is. The second thing is thermogenesis is primarily about 7% of the total daily energy expenditure. Then you have the thermic effects of food. Different foods present with different thermic effects. Some foods are better for strength training, some foods are better for aerobic fitness, and then whatever combination we could figure out is good for like your high intensity interval training or sprinting, high intense rapid bouts of energy. And then your basal metabolic rate, we'll kind of talk about it briefly here, but as far as the delineation of the two, we'll just kind of take it as it comes. The different types of metabolic mathematics used, which are the most common ones, are your Harris-Benedict, your Mifflin-St. Jeor, the Katch-McArdle, and the Frankenfield. And a lot of you are probably familiar with the top three, and I'll explain Frankenfield a little bit deeper. The Harris-Benedict into the Mifflin-St. Jeor. Okay, so it was originally used to predict the BMR, so your basal metabolic rate. And what kind of sets that apart from the RMR is the fact that the basal metabolic rate is now identified as if we were to slap a mask on you and you were to sit and wait for like an hour to an hour and a half or 2 hours, however long the clinician wants to do it, is basically your more refined RMR. Essentially, the RMR is in this video is contextually the prediction of using mathematics, who you are, the body fat you present, and gives you an idea. But the Harris-Benedict model was originally developed in the 1918. It was revised again in the mid 1980s. Then again in 1990 by Mifflin-St. Jeor. It was a former gold standard of the prediction equation. So basically, as you can tell, it's been around for a really long time. Here's the original equation. You could take it for how you want it, but as far as, if you were to ask my opinion, I wouldn't use this equation because there have been more well-defined equations since then. Again, the Harris-Benedict into the Mifflin-St. Jeor model here was, again, first because, who really did it before then? It's hard to find that type of literature. But with the Harris-Benedict getting revised into the Mifflin-St. Jeor, the regressions equations change, and so you can see that it's 10 times the weight in kilograms. Um, I'll just flip back so you can compare the two here, right? So it seems like it's more refined here, but then again here it has more relative data and more a linear relationship into its significance. So some considerations here: BMR does not equal RMR, right? And that has a lot to do with the way how the American population has changed throughout the years. And the average man and the average woman of the 1920s is not the same of the average man and average woman is in today's society. Uh, During that time frame, you had the First World War. So there was a lot of moving around and a lot of food insecurities that were going on between coast to coast here in America, not to mention the people fighting overseas in those wars. And then again, another problem with the Harris-Benedict or Mifflin St. George model is that it doesn't really account for body fat. So if you come back up here, you kind of see the weight in kilograms. Essentially, you take your weight, divide it by 2.2, gives you your mass in kilograms, then your height in centimeters, and your age in years, and you either add or subtract the coefficient with it. And another thing that really doesn't delineate these two is that it's non-gender specific either. So kind of keep that in mind. Well, it is gender specific. You got males up here and then females down here. Katz-McCardle method, however, it's simpler, it's easier to use. This one is non-gender specific. It does consider body fat in the form of fat-free mass, or abbreviated as FFM. And it does have a closer prediction associated with open spirometry, so it has a stronger relationship or correlation model towards open spirometry. And you can see the equation here is far less complex, the one up top, but to be able to calculate fat-free mass, it's a different story. Again, you take your weight in kilograms and you reverse the percent. So if you're 20% body fat, you subtract that from 1, and you're 0.8, and you multiply those two coefficients together to get your fat-free mass. Considerations here again, right? Non-gender specific. So depending on who you are, you may see that as a problem. Fat-free mass has a few flaws in its characteristics. And I mistyped this here, so I'm going to fix it. All right, so as you can see, that last bullet does state may not predict accurately. So here's an example, right? You got a male, 170 pounds, 10% body fat. By WHO standards, he is not obese. Again, we got a female, 120 pounds, 30% body fat. And you might be thinking, how's that possible? But there are people who are skinny fat. So again, WHO does not identify that as obese pertaining to age. Then you got two different populations here. You got 350-pound man with 40% body fat and a 225-pound female with 40% body fat, where you can see that the fat-free mass below is, quite concerning if you look at it as it is at face value. So keep that in mind, as the Koch-McCardle method is great and it's useful for like your active and non-obese populations, but then when you try applying it to different populations, the data may get a little skewed. So that brings me into where my research is currently with the Frankenfield proposal. Here you can see his one of his most recent articles that was published in the Clinical Nutrition, volume 32. So David C. Frankenfield, it was accepted on March 29, 2013. So it's got a little bit of headway now because it's in 2018. But here you can see that or at least I will show you that it does account for body fat. It does adjust between obesity versus non-obese populations. It is also gender specific, and it also kind of picks up where the others miss the mark. And here you can kind of see where I've highlighted the difference between obese and non-obese regressions. The top model indicates height, but if you see where the paragraph notes that height did not contribute significantly, gave a significant value of 0.228, so its correlation wasn't exactly as strong as it could have been, so they removed that from the equation and reproposed it. I say they, it's just one person, into the RMR model below that, where you see the weight times 10, age times 5, male or female, obviously, the gender there, plus 865. So when you look at it, you got to kind of read into the article. Weight is in kilograms, so you would still take your weight divided by 2.2, and then you see where it says male. Male is equated to 1, female is equated to 0. But the rest of the numbers are pretty standard across the board. And here you can see on this slide that there is a difference, right? So we take this top line here, I just basically added another criteria to this with the 40-year-old, and that's made that standard across the board. And you can see the RMR with the Koch-McCardle method is presented just below that. And just for reference here, you got the Frankenfield model, And this one, pretty much the only one that has a really defining difference. The rest of them are pretty narrow between the two differences, at least within 30 kilocalories. So you're looking at this one being the most, probably because the male does have a much lesser body fat than the other three. But then again, the correlation still sticks to being linear versus being curvilinear when you talk about having higher body fats with the Koch-McCardle method.
So as you can see, that there are several different math modeling equations here to help predict your resting metabolic rate. I hope you were able to take away one of the main facts here is that one model may be good for a sample of different people, or no, not just one model is good for the entire population. So if you need to contact me, my name is Andy. My email address is posted somewhere up here, maybe. I'm not really keen on this, but needless to say, if you need to get in touch with me, this is the best way to do it. It's the best medium. You can also leave comments or questions in the section below. So don't hesitate to reach out. I may not be able to respond to everybody initially, but here in where I'm at in North Carolina, I should have some type of freedom to be able to contact you guys. All right, thanks for watching, and hope to produce more of these in the future. Just hit the like button, subscribe. That helps me get paid, which is great. It doesn't cost you anything unless you're paying the $9.99 YouTube Red.